Good day, everybody. Thank you for joining us today. Welcome to the seminar session. A few housekeeping points to make. Please type your questions in the Ask the Questions field. And we've already noticed that there were some questions appearing before. Thank you for that. We listed them, and we will gather all the questions for Q&A session at the final part of the webinar. Also, if you experience any technical problems with regards to hearing or anything, let us know also in the same question box. Today, we'll be talking about automotive cybersecurity and future mobility. Also, we'll be looking at some issues, challenges, and future considerations that we as engineers and practitioners need to be aware of. Today, the speaking will be Dr. Madeline Cheah, who is a cybersecurity innovation lead here at HORIBA MIRA. She's responsible for cybersecurity research program with a particular interest in penetration testing and formal methods. So we are ready to go, and I am forwarding now you. Please start, Madeline.
Hi, everybody. Thank you for joining the webinar today, and I hope you'll find this a useful sort of presentation. As Victor said, my name is Madeline, and I work at HORIBA MIRA as Cybersecurity Innovation Lead. And today I wanted to talk to you a little bit about automotive cybersecurity and future mobility. Future mobility is one of those really interesting words at the moment because we're not just talking about cars or trucks or things, machines that take us from one place to another, but actually how we plan our journeys and what the ecosystem can do for us in terms of those journeys. And that has some quite profound cybersecurity implications. Before I get on to the next bit, for those of you who aren't aware, HORIBA MIRA is based in the Midlands in the UK. We're an advanced engineering consultancy and test company, basically working with many manufacturers on such issues, actually. So, on to the next slide. Before I start talking about cybersecurity in earnest, I wanted to bring together a little bit of terminology just so we're all on the same page. In this case, we want to be talking about cyber-physical systems. For those of you who have had experience in cybersecurity, usually in the IT side of things, we look at privacy issues and data protection issues. For those in the sort of more mechanical side of things, possibly the cyber issues might not have been so apparent before, especially in terms of the trends that we're seeing in this last decade, really. So I wanted to introduce this whole cyber-physical systems aspect. And really what this is the integration of the computational elements, i.e. the cyber elements, with the physical elements, so the mechanical and sort of electronic elements that we're used to. With some networking elements, which provide feedback from the cyber and the physical layers, into a cohesive system. And this is what we call a cyber-physical system. Now, those of you who've been in mechanical engineering for a long time obviously are very aware of the safety aspects of it. And the cyber part of this cyber-physical system actually adds another dimension. It's just another entry route into causing safety problems. For those who are in cybersecurity but not so much in the physical realm, and for those of us who entered into this area from the cybersecurity point of view, it's also in addition to privacy and data protection and identity fraud aspects, we're also having to consider safety aspects now. And it's definitely a really interesting field. The next slide covers what I think of as cybersecurity in a picture. It's one of my favorite pictures of cybersecurity. And as you can see in the middle here, might be very small for some of you. Hopefully you can zoom in and have a look at it. But it's a barrier. And as you can see, it's a very good barrier. It probably works exactly as it should. Unfortunately, it does exactly as it should, but people find ways around it anyway. So these are my security exploits analogy. And of course, you can see their tracks in the snow, so you can see them. These are the ones we know about. But of course, there's plenty of others that we don't know about, that we can't track, that may have never happened, but we still need to consider. Now, in terms of system design, whether it's in mechanics, electronics, or purely in the cyber world, one of the things that we really want to look at usually is making it infeasible for someone to exploit. Cybersecurity, like all security really, is about making things infeasible, making it so difficult that they give up and move on elsewhere. So this is something that we are looking at in terms of the cybersecurity perspective. So, the last sort of set of definitions that I wanted to look at was, is anyone else having sound problem issues? Right. So the last bit that we wanted to look at, or the last definition, is CAV enablers, or connected autonomous vehicle enablers. And I'm wanting to look at these enablers because the autonomous vehicle is going to be key to the sort of future mobility question. We're probably going to have all sorts of other types of machines and all the other types of machines and other aspects to future mobility, but the autonomous vehicle is going to be key to it. And key to enabling them is artificial intelligence. Now, what we do know is that it will be key. What we don't know is how much of it, where, in what use cases. There's a lot of research out there and a lot of work out there, absolutely. But it's something that we're not quite sure of yet in terms of its mass deployment, where it's going to be placed, how it's going to be designed, and what would give us the best guarantees of safety. Not just onboard the vehicle, we also have off-board computation that will probably be needed because systems on vehicles or other kinds of transport will probably be quite constrained compared to the sort of bigger computing power, the larger computing power that we've come to expect from laptops, desktops, and servers. So there's that interaction with artificial intelligence to kind of really think about as well. Sensor technologies, as we know, there's a whole array of sensor technologies in terms of the types of things that are needed on a vehicle to sense its external environment. So there's another enabler there. Connectivity, something that enables the vehicle or the autonomous system or the robot, whatever it is, to take in information beyond its immediate environment. Also a key factor in predicting, forecasting, etc. Underlying it all is data, really, really important. Having the right data, having the right amount of data, knowing what to do with the data and how to process it will be absolutely key to autonomous systems. And the last one that really is more like a layer above, but something that I'll address a bit later from a cybersecurity perspective, is public trust and acceptance. And this is really important because obviously as manufacturers, engineers, designers, practitioners, etc., we don't have public trust and acceptance, we're not going to be able to sell anything, and therefore we aren't going to be able to make any money. And there are technical ways to kind of really enhance this aspect of what might seem at first glance a very social issue. The other area around cyber-physical systems that I wanted to bring up was balance. Cybersecurity, and I'm sure like many other things, is a balancing act. And in this case, one of the balancing acts is around constrained systems, as I mentioned earlier. So in terms of the best defenses we have for cybersecurity currently, a lot of it is very computationally expensive. So let me give you an example. Cryptography tends to be so computationally expensive that it introduces latency. Now, in real-time systems or in systems that need real-time responses, we're not going to be able to afford such latency. And this is not just true of manufacturing or of vehicles, but of things like medical systems. So that's one of those balancing acts we have to be aware of from a cybersecurity perspective. Life cycles are another one. I say long life cycles, I mean it's relative, isn't it? But long life cycles compared to cybersecurity, where the IT industry and possibly even the mobile phone, the apps industry, all of these industries and sectors are used to updating on a very regular and a very fast-paced environment, whereas the average design life time of a car is about 7 years. And we are expected to, these cars are expected to be on the road for another 12 to 15 years. So it could be a good 20, 25 years from the time that the design of a car is conceived to the time that it leaves the road, before it isn't part of the fleet anymore. And from a cybersecurity perspective, this has many, many different implications, and I'll be going into it a little bit later. The supply chain, or the supply mesh, shall we say, seeing as it isn't really so much a chain anymore. But upstream and downstream is something we need to consider. And I know there's a lot of talk right now on cybersecurity in Industry 4.0, smart manufacturing, all the rest of it. Cybersecurity is an overall system property. It's also a holistic type property. It needs many factors considered in balance with each other. And in terms of the supply chain, really, your system is only as strong as its weakest link. And if that weakest link is introduced somewhere in that mesh or that chain, then we're going to have an end product that's insecure. The supply chain downstream is one thing, but the supply chain upstream is something else. So dealerships at the moment are in a position where they are holding onto some of the manufacturer's reputation, but they may not belong to the manufacturer at all. They may be franchises, subsidiaries, and so forth. They're also kind of the first port of call, a bit like your frontline IT system, for any problems that may occur in the wild, so any attacks that may occur or any thefts that may happen. And because of that, they also need to be considered in the whole cybersecurity ecosystem. Furthermore, because of all the connectivity that I mentioned earlier, we're seeing cars being turned into almost data centers on wheels, which means all that data is now going somewhere. Now, might be straight back to manufacturer, might be straight to a third-party data controller or data processor, or it might be through the dealership for things like diagnoses and quality problems and so forth. And all of these things have cybersecurity implications that need to be protected. We've also got legislation. So legislation here has several layers. Now, legislation specifically for the automotive or autonomous vehicle is pretty much emergent. Lots of countries are talking about it. Drafts are appearing for comments and so forth, but there isn't really any out there at the moment, specifically to cover all aspects of the autonomous vehicle. But beyond that, what we're actually seeing also is legislation that was never really meant to apply to a vehicle, but because of these mega trends of connectivity and software-defined everything, we're actually seeing a lot of sort of generic legislation that applies. So an example is GDPR. Not really, I'm sure the policymakers weren't really targeting or didn't really have the use cases of the automotive or autonomous vehicle in mind, but because now they're collecting data and collecting private data, we have to consider it. There's a whole raft of IoT legislation coming out as well, and in some cases, these policymakers reference connected cars as part of this IoT space. In some cases, they implicitly say that connected cars are part of it, and in some cases, they're not part of it. So, you know, this mesh of legislation, this layer that really wasn't meant for vehicles, but are now part of it, would also need to be considered. So those were all the questions and some of the answers that we do know. Some of the known unknowns are also there. But the next set of slides cover the sort of almost unknown, you know, what we actually don't quite know or don't quite have a handle on yet, but know that it might be a problem in the future, especially in the realm of future mobility. And this is where I wanted to introduce to you this Internet of. Now, we know about the Internet of Things. It's been a buzzword, something that's been out there quite a lot. And I wanted to posit that the Internet of Vehicles is actually a superset of the Internet of Things, the Internet of Vehicles being these connected, semi-autonomous, in the future, fully autonomous vehicles. Not just vehicles, but other machines, other modes of transport, that these Internet of Vehicles are a superset of Internet of Things because they're made of many, many things. But that this Internet of Things is actually a subset of the Internet of Everything, or what I call the Internet of Everything, of which things is a pillar, but only one of many pillars, the others being data, process, and people. And these 4 pillars need to be considered from a cybersecurity perspective, otherwise we're missing out on quite a lot, and potentially providing a gap through which someone can exploit. So this is what I'll be talking about in the coming slides. So we have a lovely car here, and we have an Internet of Things, or things to consider. And going from the sort of early cybersecurity work, or kind of introducing early cybersecurity work, I'm very sure that many of you know about the CAN protocol. It's considered a legacy protocol because it was implemented a couple of decades ago, but it's deployed everywhere, and not just in cars, in some medical devices, in ships, in planes, so very well used protocol, and has had demonstrated attacks against it, mostly because of its status as a legacy protocol. So these attacks include injection of signals, replay of signals, spoofing of signals. Some of the earliest work in terms of looking at the cybersecurity implications have been looking at the CAN bus. We also have the OBD2 port at the moment for those who are involved in trying to get rid of car theft, the sort of bane of their life in the sort of early stages of awareness of cybersecurity. But for those of you who don't know, it's a diagnostics port, mandatory in pretty much every country, and a car is not sold without it. It was meant for diagnostics, troubleshooting, that sort of thing, but of course, being as that port had to be there anyway, manufacturers started to make it multi-use, and that included things like programming of new keys, which then criminals exploited. Immobilizer, another early sort of demonstrated exploit around car theft and how you can use overrides and or replace it completely. Keys are another one. So the most recent spate of car thefts are around what we call relay key attacks, which look at relaying a signal greater than what you would normally expect. These tend to target the passive key entry systems, the ones where you only need the keys to be on you somewhere. You don't have to actually use them, and you can then unlock the car and or start its engine. The relay attack, its end result is to amplify the distance between key and car. And this has been used, and we can see very many articles in the news and things about that. Moving on from there, I wanted to bring in the CD player. Now, this is actually an exploit demonstrated by a researcher in the US, and usually it's quite old. It's from 2010, 2011. But I usually bring this in to give an example of a vehicle example of the picture that I showed earlier around cybersecurity. So what these researchers did, they put together a piece of malicious code onto a CD. They encoded it as a music file. They placed it in the CD player, and the CD player did exactly what it was meant to do. It played the music, but by playing it, it actually executed some code that allowed them to reflash that particular ECU, and from there move on into the rest of the car. And this is a great example actually of excessive functionality, or functionality beyond what was expected, and it's something that we would definitely need to watch out for if we were designing systems. Wi-Fi, relatively low-hanging fruit. So lots of examples out there of how Wi-Fi can be used maliciously, and actually in terms of looking at vehicles, I've looked at some myself, and there's been quite a lot of information that you can glean from Wi-Fi, including information that can be used to intrude upon a car, not just to exfiltrate data. Cellular, so the infamous Jeep chase was using the cellular connection, and the danger in this, of course, is that it's a long-range connection. So with regards to that particular case, or that particular demonstration, the researchers set up a base station that basically allowed them cellular access through cellular means to many different cars. It's also got interesting implications. For example, from April 2018 in the EU, every vehicle must be sold with telematics, every new vehicle, and telematics implies a cellular connection. So we've had some things, sensors, some demonstrations of ultrasonic spoofing, some demonstrations of jamming, and so forth. So we've had some things, and these were all pretty much early work, around 2010 to 2015. But I wanted to talk about more things, things that are possibly going to happen in the future, because they may not have had a demonstrated attack in the vehicular environment, but they have been demonstrated to have weaknesses technology-wise. So one of those, for example, are around predictive management systems. Now, earlier I mentioned that a key enabler was artificial intelligence. And there are lots of issues with regards to artificial intelligence and what you can do with the data set, for example, poisoning it, making sure it drifts a certain way or has a certain bias. And this will affect things like predictive management systems. Now, one of the areas of predictive management systems is battery management systems, and of course batteries are a safety critical aspect of any vehicle, and it's not something that we want to something that we want to leave a gap in. For those interested, there is a white paper I've written on cybersecurity battery management systems that we can circulate the link to around later if you like. But yes, so that's an example of that. We've got telemedicine. I say telemedicine, really I mean in-cabin monitoring, but already we are seeing much activity around how to monitor the driver or the occupant for being drunk, for being tired, for being drowsy, for being stressed or angry, and all of this obviously doesn't just have security implications, it has privacy implications as well. And beyond the privacy implications, I mean, we want to make sure that public trust and acceptance are there. I want you, my audience, to imagine if you would be comfortable, for example, to have a camera pointing right at you from 3 feet away as you're riding in this autonomous vehicle to where you're going. So this is something, design-wise that we would want to consider as well. We've also got wireless charging or perhaps charging in any case. So now we're seeing financial transaction systems actually with this charging being introduced into the vehicle. And as we all know, where financial transaction systems go, criminals usually follow. They follow the money. Lots of talk and activity, and actually already deployed in some vehicles, peripheral devices, for example, smartphones as keys. The smartphone and its connection to the car being used to even auto park the car, for example. So lots of cybersecurity implications there. And an example also of how the boundaries of the vehicle is ever increasing. So before, we only really had to worry about protecting the vehicle or protecting the component physically. And now we've added the smartphone, and if the smartphone is compromised and is then able to compromise a car, or if the charging infrastructure is compromised and is able to compromise the car, or if the car is then used to compromise infrastructure in itself, we've got to start considering all these connections outside of the vehicle, which adds to the complexity, definitely. Personal assistance, so this is an early example of artificial intelligence already being deployed inside the vehicle. Here we have, in America, there are certain car manufacturers who've already introduced Alexa into their cars. And one of the demonstrated attacks around Alexa was being able to give it covert instructions via ultrasound, which again goes back to my picture of going outside the intended functionality. I mean, we can't hear ultrasound, but apparently Alexa could, and we never thought to test for it. Been patched now, but it's just an example. Telematics I mentioned earlier, and off-board computation I mentioned earlier as well. And this off-board computation just means that the car itself can be used as a vector for many other things. So we want to consider how we can make sure that things don't, that the car itself can't be used to impact something else. Otherwise, reputationally and safety-wise, it would not be a great outcome. Cabin monitoring, I think I've mentioned, and external monitoring. So not just the ultrasonics or the GPS, but now we've got camera, radar, LiDAR. We've got multiple layers of sensors and very complex sensor fusion algorithms going on, especially going into the future, when it also mixes with the signals that it will get from connectivity from further away. So lots of complexity there, and different networking protocols. So where before we had CAN as a legacy system, now we're seeing different networking protocols being introduced into the vehicle with different needs, different requirements, and also actually probably bringing in weaknesses from traditional Ethernet and traditional Internet protocol. And what we must ensure is that we also port over the defenses at the same time. So that covers things, I think. And moving then on to data. So in this case, don't have to read everything all at once. I'm sure the slides can be made available afterwards for those who are interested. In terms of data, here I have an example of how data could be used in machine intelligence or machine learning. Down the left side where area is, deduction, knowledge representation, planning, learning, these are all the things that we would use machine intelligence for in both the autonomous vehicle space and elsewhere. And what I really wanted to highlight here is that we can use it both as defense and as offense. By offense, I mean the criminals can use it as offense. And what's interesting is that you can see that the techniques are exactly the same, that they want multi-agent planning and cooperation. It's just that the aims are different. Where we would want path planning to be safe, probably an attacker or a malicious adversary would want to make sure that path planning is unsafe. And as we go down that list, you can see how they play off each other. And one of the trends that we're going to see is probably an arms race, because the criminals know as much as we do. They mirror everything that we do in terms of trying to make money, and I'll cover that a bit later. And they actually move a lot faster than we do for many reasons. One of them, for example, is that they don't need to follow laws, they don't need to follow paperwork or ethics. If they want to do something, they just do it. So they move a lot faster. The other is what I call the sword and shield, or what's known as the sword and shield principle, in that defenders tend to have to defend everything, whereas an attacker only needs to find one thing. And that also makes them a lot more flexible and agile, so just something to keep in mind. Moving then on to what I've called the data jigsaw. So this particular thing looks at, what pieces are there? What are the pieces that we know, and how do they fit in with the pieces that we don't know? So based on, incidents like car thefts, we know some of the targets. We know some of how they are going to enter or intrude upon that system. We know some of the methods that they're using, especially for car theft, because they are a real-world event, and therefore lots of interest, lots of money goes into investigating these things. We know some of the patterns that they use for this. So if relay attacks are nice and easy and get you very expensive cars, then that's what they'll do. We know some of the attack actors, so who would do certain things like this. Now, remember though, what we do know is based on current vehicles, not on autonomous vehicles. So we know some of the motivations. Actually, it's money. I mean, when is it not money? But there may be other motivations beyond that. What we don't know, attacks in the wild. By attacks, I don't just mean the ones that result in car theft. I mean the ones that result in safety problems on the road, in your infotainment system malfunctioning, in things cutting out and coming back on randomly. Now, the reason why we don't have such data is because we don't have any forensic system design. So by forensic system design, I mean a design that allows for events to be logged so that we can trace back what happens. Now, there is the event data recorder, but it only holds a few seconds. It's meant for accident reconstruction or for information into accidents, and only has small things like whether you have your seatbelt on or whether the airbags were deployed. So if someone was injecting CAN data into your car, it wouldn't be something that would easily be recorded. And because of that, usually a lot of the mindset tends to be around fault rather than malicious fault or maliciously induced fault. And this comes back to my point about dealerships and sort of frontline first responders who would then also see fault rather than maliciously induced fault. So this is something that we really would need to look into. We also don't know the real-world effects at scale. So the scale part's really important because there are lots of traffic simulations for future autonomous vehicles and future mobility, lots of sort of multi-agent interaction type studies. But, in the real world, with certain weather conditions, with certain events happening, how many cars would it take to gridlock a city, for example? These are not answers that can easily be deduced without knowing about attacks in the wild and without having the the right designs to be able to record that information in the first place. And not just at the vehicle level, but also at the city level. There's also a lot of implications with regards to forensic system design, by the way. So anything with added computation to deal with added data being recorded or protecting that data. Remember, I talked about cryptography earlier being computationally expensive. All this adds weight, needs added power. It adds to probably wiring, unless you can find some way to make it wireless. It affects harness design then, and then it'll affect, you know, lightweighting efforts and emissions and all the rest of it. So it's a big sort of balancing act. In terms of where the boundaries are, we don't know. They're ever expanding. So from the car, we've got the car to the charger, the payment system in the car to the fuel station or where you want to buy your coffee. We got Alexa. We've got cars with Alexa integrated, and Alexa is then connected to the cloud, which is basically everything then. The car connected to your phone then connected to the cloud. So we can see the boundaries are becoming ever more fuzzy, and actually bears out what we see in other industries like IT, where this is more mature, is this concept of decentralization, so that there's no longer a single controlling entity for that particular system, and also deperimeterization. So the perimeters are not so clear anymore, and in fact, you probably end up with no perimeters in some cases. That's not to say that we can't scope out projects and problems to investigate, but just to be aware that, you know, this adds to the complexity of what we're trying to do. We have no metrics. This is a really basic requirement if we wanted to benchmark or talk about boundaries or measure anything. And unfortunately, because cybersecurity attacks originate with a human, metrics are quite fuzzy. So all the risk analyses that you see, whether from more mature sectors or not, tend to be around qualitative metrics. So, you know, would it take an expert to do this? But then let me ask you this. Is your expert the same as mine? There are some areas where they talk about, you know, the highest level of difficulty being one that needs multiple experts. But they don't say whether it's multiple experts in terms of the same discipline, so 2 people, or whether it's an expert in electronics and an expert in cyber and an expert in hardware. It's not clear. There are other areas also, things like motivation, which is very difficult to measure, and all of that affects the physical metrics that we could possibly perform tests for safety, for example. So because we have no metrics, and because we don't know where the boundaries are, and actually we don't know much at the moment with regards to the real-world effects, we have no trust. So that's the data jigsaw there. Now, moving on to process. Process helps glue data and things together. And in this case, what we have now is some sort of process for security assurance. Actually pretty good at this in the engineering, all the engineering industries. Security assurance, risk assurance, safety assurance. And as you are probably aware, I mean, this includes things like standards and best practice, testing for validation, all kinds of analysis. This gives you confidence, but it's important to remember that it doesn't give a guarantee. And especially for cybersecurity, whatever testing, analysis, standard, certification can be done, it's only ever a snapshot in time. SSL, which is a protocol for encryption over the internet, was considered very secure, and it was considered mature enough to have good security, or good enough security, for the better part of 20 years, until it wasn't, when an attack called Heartbeat was found. So never a guarantee, gives you some confidence, but in the cybersecurity world things can change, and that's because the exploiters, the criminals, are looking for the unexpected. Nobody designs a system to be insecure. So whenever an insecurity is found, it is always unexpected. So we just have to remember that, take that into account. Security governance, now this is emerging, as I mentioned before, with regards to things like legislation. In other sectors, there's things like monitoring to make sure that incidents can be responded to very quickly. We've got compliance, monitoring, auditing, that sort of thing, how to manage the information, manage all the security aspects, manage the security processes. deterrent. How do you keep someone from doing what it is that they don't want, what it is that they want to do? Now, it's emerging in the automotive industry and actually emerging in the cyber-physical world, but we can take learning from the sort of IT industry, especially in terms of how we manage this information, how we gateway with other experts or other teams so that we don't have a siloed mentality. Knowledge sharing is very much part of what cybersecurity is about. And the last bit, and this is the bit that we still, not quite sure about, refer back to my data jigsaw and the missing pieces, is processes for conflict resolution. Now, in terms of cybersecurity, there is actually quite a few conflicts with some of the fundamental aspects that you would expect from engineering cyber-physical systems. So the first is security and safety. Now, a system can't be safe without being secure, because if it's not secure, someone could maliciously induce a fault that affects safety. So they do overlap. But there are also conflicting requirements. And here's an example. In the safety world, for anything that's safety critical or mission critical, probably you want to make sure that the time it takes for a response or mitigation is as tiny as possible, real time as if possible, for things like brake signals. Now, for security purposes, we want to actually make sure that there's someone there to sense check. So in effect, safety takes human out of the loop because humans are too slow. We want to automate it, make it as tiny as possible, as real time as possible. So security purposes, we want the human back into the loop to check that it makes sense, that the brake signal hasn't been induced by someone else or injected by someone malicious. So there's a bit of a conflict there, and even though there may not be a resolution, it's a balancing act that we need to be aware of. Security and privacy is another one. Again, privacy cannot be guaranteed or cannot be provided really without security in place. But they also conflict mostly because of the monitoring aspect. If you have to monitor and log everything, then we end up with privacy being an issue. Security and usability. So from a cybersecurity perspective, this is a whole age-old argument that the more usable you make something, the less secure it is, and vice versa. The more secure you make something, the harder you make something to use. And this could be something as simple as having to press in 10 keys before you get into your car, probably why the sort of keypad entry type stuff didn't ever come off. There's also a whole raft of usability legislation for areas like the medical industry, just to make sure that doctors or nurses or lab technicians aren't, having to try and figure out really difficult concepts to be able to use it. In future mobility, it's very interesting because there is no form of transport, whether in automated mode or not, other than what we see as fully autonomous vehicles. There is no other form of transport that does not have a trained operator somewhere in control or at the helm, ready to take control if it's in automated mode. So whether it's a train, a ship, an airplane, there's always a trained operator there. Now, in a fully autonomous vehicle, as we envision it in the future, there won't be anyone there. So usability-wise, what are we going to do? How do we tell people to respond in an emergency? Is there going to be a remote operator? Will the remote operator even be human? And how do we communicate that? Do we even communicate it? So lots and lots of questions there. Security and cost, and this is the last one. Security can be seen as a cost center, the same way that safety was seen as a cost center. But in and of itself, security can be a competitive advantage because legislation is coming, we know that. And also, it can be a marketing tool the same way that safety was to Volvo a few decades ago. So it's one of those areas that we can look at it as getting competitive advantage, or we can look at it as a cost. I mean, again, obviously there needs to be a cost-benefits analysis and all sorts of balancing acts, but that's a really important one to consider as well if you're in charge of managing these sorts of processes. And now we come to people. So in this case, I just wanted to give examples of how the criminal platforms are already mirroring what we see in the more mature sort of IT and ride-hailing, whatever industry. So we've got, data as a service, cloud as a service, and the criminals have crimeware as a service. They've got, rental of computing resources and being able to buy or hire someone to write malware for them. They've got paper install, they've got crimeware toolkits off the shelf, brokerage, brokers and data suppliers, exactly the same way. They work exactly the same way as we would to supply software and support and data. Just that their purpose is for criminal purposes. And I wanted to highlight this because they haven't yet turned their attention to future mobility. But if we can see the benefit and the opportunity in future mobility, so can they. And I just wanted to bring up this number here, $1.5 trillion. This number represents the revenue generated by the global cybercrime economy. It is nearly twice the value of the illegal drugs trade. And with that sort of opportunity, I don't think they're going to keep away for long. So cybersecurity is definitely something we want to consider at all levels, whether it's hardware, software, or the mechanics around it. The web of profit is, if you Google that, it's public, and you can read through how this researcher broke down such numbers. 1.5 trillion is an at least number, at least 1.5 trillion, because the researcher, the author, could only get hold of data for really high-profile stuff like ransomware. But it's an interesting read. The other one, the one that would probably affect us most, is this other number, which is the estimated damage annually, estimated in 2019. And again, this comes back to not just the vehicle, but all the things surrounding the vehicle, all these services and apps and applications and whatever it is else that we want to offer, that the damage will just be growing if we don't protect it. So that's one aspect of the people. That's the criminal aspect, kind of telling us why it's important to do what we do. But the other one is about data. Coming back to data, but not just data for the sake of functionality. This comes back to public trust and acceptance. How do we make people comfortable using such things? I mean, all of these headlines, for example, they're not really illegal. They're not against the law, really. But thinking about them makes me uncomfortable. It makes me not want to engage. And without the diversity of engagement and without the diversity of engagement and without the idea that we want to make people feel comfortable and protect this sort of privacy, not just where they've been or how much fuel they've used or how much money they've spent, but also this sort of thing, seeing as future mobility is going to be intertwined with every part of our lives, if you believe everything that's being said out there. We want to make sure that this is considered. I brought up DNA data breach as well, just to bring up very, very briefly some of the issues around biometrics and the use of biometrics, because I can change my password quite easily if there is a data breach, but I probably can't change my DNA. And this is where, some of the discomfort happens as well. So that's another aspect of people. And the last aspect of people that I wanted to speak about was skills. There is a shortage of skills in every industry for cybersecurity. I went recently looking for some statistics on how many people were needed, and currently globally it's about 6 million in terms of the demand. And as of this year into next year, there were 3.5 million vacancies. We're missing more than half the people that we need. And this is an estimation with 0% unemployment. So that is anybody who has any kind of cybersecurity training or education is now in a job, and we're still missing more than half. So little plug here, by the way, at the MIRA Technology Institute, we do run automotive cybersecurity courses if you are interested. It's something that is fascinating, and as you can see, very good employment prospects. And yes, so lastly, really just to summarize, we have the everything part. So casting our mind back to things, still largely unregulated. There are bits and pieces coming out. Quite a lot of it's in the USA, for example, going through the House or the Senate. And what's interesting about these things is that the applications and technologies are kind of proliferating, converging, and conflicting. So sometimes I give talks on IoT rather than on future mobility, and some of the items that you see with internet connections are kind of mind-boggling. So we're seeing toilets, washing machines, toothbrushes, kettles, Barbie dolls. Do we really need them? Something to consider. And also legacy systems and requirements. Now, for the automotive industry, we count that in terms of decades, so 7 to 25 years or so. There are other industries, of course, where this is more of an issue. For example, the maritime industry, ships are expected to be out there for about 50 years. When we come to looking at infrastructure and how we can make smart motorways and smart cities, we expect those things to last for decades. Now, I didn't mention this particularly in this presentation, but realistic quantum technologies are expected in the next decade or so. We've heard recently in the UK that the government plans to ban any combustion engine-based passenger vehicle by 2035, so 15 years, which really is only about 2 car generations. So, lots of things to think about there in terms of legacy systems and requirements and the cybersecurity implications. The data part of it, as you can see, we're still missing quite a lot of pieces, and this is one of the things that I work on in terms of my day job. And also, we want to be aware of the quality of the data that we're getting, and also the fact that correlation is not causation. This is something that does pop up quite a lot in other industries where artificial intelligence is used. We, of course, want to make sure that there is some bias, bias towards safety, for example, but we need to balance that out with good quality data, making sure that everything is optimal. And actually, my hunch is that prediction and that what we see in cybersecurity may not be measurable by a single variable. But then we can't know for sure because we're still missing so much of the picture. We also have process. So in terms of that, things and data would be disconnected without a process, but we need to cover many aspects that seem outside of the vehicle or outside of that particular system. I would even go so far as to say if network connectivity is introduced, then we need to make sure that the boundaries are extended further beyond that particular system. And also because security is an overall system property, it's only as strong as its weakest link. And here's another sort of motto that I like to go by, which is whatever makes it convenient for you or for a customer also makes it convenient for an attacker, unless you protect it properly. And the last is around people. So, we want to consider multiple angles of people, want to consider who might take advantage of what, who would benefit from what, and, who do we need in terms of protecting these systems. So, really, that's pretty much the webinar. I think we have a few minutes for questions. And thank you very much. Those are my contact details there. Please do let me know if now and or later you have anything that you want to add or ask.
Okay, we are about to begin the final part of the webinar, the Q&A session. We've received some very interesting questions, and let us go through them. But let us begin with the questions regarding organization. At the very first slide, the question was asked: will the slides be circulated afterwards?
Yes, they will.
Okay, fine. So now we are over this. Let's talk about this about the topic. At slide 14, when we're speaking of data and people, what industry standards exist covering cybersecurity?
If we're talking information security, then there's standards such as ISO 27000. I say standards, it's actually a family of standards. There's quite a lot there. There's standards around infrastructure security, so that would be IEC. There's also the upcoming standards for road vehicles, security engineering for road vehicles, which we at MIRA are involved with, called ISO SAE 21434. If you are in the automotive industry, there's already some guidance and a guidebook called the SAE J3061. So those there should give you a starter for 10. But yes, in terms of the ISO standards, depending on the industry that you're in, there may be lots or few. Some of them are laterally applied. So information security was really looking at IT systems, but because now we're holding more information on the car, more information on whatever devices we're using, it kind of applies to everything that can be considered information. So I hope that helps.
Okay, at slide 10, when you were talking about arms race between the cybersecurity specialists and the criminals, the question was, how can we address the problem of cybersecurity criminal activists, specialists, working faster than the legal cybersecurity specialists? What do we do to win this kind of unfair race?
By working together, so by knowledge sharing. For example, antivirus companies share everything about malware with each other because they know that there can be no good for anybody to have malware out there. Well, how they do differentiate is based on the service, the user interface, how quickly they respond, the support helplines, and on price. But the technical details of malware is shared, and that's how we can address the speed that they work at by working in concert together, so that we're not duplicating or unnecessarily reinventing the wheel.
Very well. So at the slide with the barrier at the very beginning, the question was, is it physically possible to create a system that will take into account all the potential vulnerabilities?
I'm sorry, could you please repeat that question?
Is it physically possible to create a system that will take into account all the potential vulnerabilities?
No. There's no such thing as 100% security. There's only what we might consider acceptable security. And that's why we want to be working towards methods of risk analysis and other kinds of analysis to give us some assurance that things are acceptably secure.
All right. At the slide 5, there was a question that you partially already answered. It was when you mentioned the supply mesh. So if making the vehicle secure is important for everybody involved during production process, should the cybersecurity effort be done together with all the parties involved? Is it possible without compromising the valuable data?
Yes, it is possible, although I would say in terms of knowledge sharing, a certain amount of disclosure needs to happen. But that's not to say we have to disclose every single bit of IP that we own. But that amount of knowledge disclosure would then be proportional to the cybersecurity requirements that you might then be able to put together that covers more of the gaps. It's all about optimizing coverage of the gaps. Granted, sometimes we don't know where the gaps are, but that's why 2 heads or more are better than 1.
Okay. During the many moments of the presentation, the audience expressed interest in the white paper you mentioned. Could you mention some information about accessing it and generally some words about this?
I can actually say, through the IMechE or perhaps through the IMechE, or perhaps if you email me, as you have my contact details up on the screen right now, I can send you the link. It's publicly available. All
right. So we've reached the end of the questions. So if anybody has any important questions, we still have a moment of time. So please ask them now. And if not, if there are no further questions, or you want to ask them directly to Madeline, please, as Madeline said, contact her on the details visible there. And thank you very much for being part of this webinar. Thank you, Madeline.
Thank you.